Today we are going to learn about mastering feature scaling in Scikit-learn. We will explore the importance of feature scaling, different scaling techniques, and how to implement them effectively using Scikit-learn for optimized machine learning performance. Welcome to our journey on mastering feature scaling using Scikit-learn. Feature scaling is a crucial pre-processing step in machine learning that involves adjusting the scale of features to ensure they contribute equally to the model's learning process. Without proper scaling, some features might dominate others due to their scale, leading to skewed model performance. In this video, we'll explore different scaling techniques like standardization and normalization, and understand their impact on various algorithms. We'll also dive into Scikit-learn's tools that make feature scaling straightforward and efficient. Let's get started.
Feature scaling is vital because it ensures that all features contribute equally to the model's learning process. Without scaling, features with larger ranges can dominate the learning process, skewing results. This is particularly important for algorithms that rely on distance measures, such as k-nearest neighbors or support vector machines. Proper scaling can improve model accuracy, speed up convergence during training. It also reduces computational costs by normalizing the data, making it easier for algorithms to process. By the end of this video, you'll understand the significance of feature scaling and how to apply it efficiently using Scikit-learn. Understanding the differences between standardization and normalization is key to selecting the right scaling method. Standardization, or z-score normalization, centers the data by subtracting the mean and scaling to unit variance. It's ideal for algorithms that assume a Gaussian distribution of features. Normalization, on the other hand, scales features to a fixed range, typically 0 to 1, and is useful for algorithms that need bounded inputs. The choice between these methods depends on the algorithm you're using and the nature of your data. We'll explore these techniques in detail and see how they affect data distribution and algorithm performance.
StandardScaler in Scikit-learn is a powerful tool for standardizing features. It adjusts data to have a mean of 0 and a standard deviation of 1. This process is essential for algorithms that assume normally distributed data, such as linear regression. To implement StandardScaler, you can simply import it from Scikit-learn, fit it to your training data, and transform both the training and testing datasets. This ensures that the scaling parameters are learned only from the training data, preventing information leakage. We'll walk through a code example to demonstrate how to use StandardScaler effectively. Min-max scaler is used for normalizing data by scaling features to a specific range, usually between 0 and 1. This technique is particularly useful for algorithms that do not assume any specific distribution of data. Min-max scaler applies a linear transformation to the data and is advantageous when the data does not contain outliers. We'll demonstrate how to implement min-max scaler using Scikit-learn. You'll see how to fit the scaler to your training data and transform your datasets accordingly, ensuring that the scaling parameters are consistent across the training and testing data. Robust scaler is an excellent choice for datasets with outliers. Unlike standardization and normalization, robust scaler uses the median and interquartile range, IQR, to scale data. This approach minimizes the impact of outliers and reduces skewness, making it ideal for datasets that are not normally distributed. In Scikit-learn, implementing robust scaler is straightforward. By fitting robust scaler to the training data and transforming both training and testing datasets, you ensure that scaling is consistent and robust against outliers. We'll go through a practical example to see how robust scaler is applied in a real-world scenario. In this section, we'll dive into practical examples, showcasing how to implement feature scaling using Scikit-learn. We'll start with a code walkthrough for StandardScaler, demonstrating how to standardize features for a simple dataset. Next, we'll apply min-max scaler to normalize data, explaining each step and interpreting the results. Finally, we'll explore robust scaler through a real-world application, highlighting its effectiveness in handling outliers. By the end of this section, you'll have a clear understanding of how to implement these scaling techniques and interpret the transformed outputs for improved model performance. Feature scaling can significantly influence the performance of various machine learning algorithms. For instance, distance-based algorithms like k-nearest neighbors, KNN, and support vector machines, SVM, are highly sensitive to the scale of input features. Proper scaling can enhance their accuracy and efficiency. Similarly, scaling impacts the convergence speed of neural networks and improves the performance of logistic regression models. In this section, we'll conduct a comparative analysis, showcasing how different scaling techniques affect these algorithms and how you can leverage feature scaling to optimize your models effectively. To make the most out of feature scaling, there are several best practices you should follow. Always fit the scaler on your training data, not the entire dataset, to avoid data leakage. Choose the appropriate scaler based on the data distribution and algorithm requirements. For example, use StandardScaler for Gaussian distributions and min-max scaler for bounded inputs. Handle categorical features separately, as scaling is primarily for numerical data. Finally, monitor your model's performance to ensure that scaling is having the desired effect. By adhering to these practices, you'll be equipped to implement feature scaling effectively in your machine learning projects. While feature scaling is a powerful tool, there are common pitfalls that can undermine your model's performance. One major mistake is data leakage, which occurs when scaling parameters are derived from the entire dataset instead of just the training set. This leads to overly optimistic model evaluations. Additionally, ensure balanced feature distributions to prevent bias scaling. When handling unseen data, apply the same scaling parameters to maintain consistency. Lastly, validate the impact of scaling on your model's performance to ensure it aligns with your goals. By being aware of these pitfalls, you can avoid them and achieve optimal scaling results.
As we conclude this video on mastering feature scaling in Scikit-learn, let's recap what we've learned. We've explored key scaling techniques, such as standardization, normalization, and robust scaling, and their implementation using Scikit-learn. Proper feature scaling is crucial for enhancing algorithm performance and ensuring accurate model predictions. We encourage you to practice these techniques with your datasets and observe their impact. Thank you for joining us on this learning journey, and we invite you to explore further topics in machine learning to continue expanding your skills.